In this section, we're going to learn how to work with the equations of lines and planes, look at their graphs, and do various problems involving both lines and planes. And we're going to start with lines. And so what we have to do at first is understand the idea of a vector equation. All right, so one of the things that you learn about in previous courses is how to write out a parametric equation. Okay, so here's an example of a parametric equation that you might have seen before, like x is equal to x0 plus at. Okay, where the idea is x0 and a are just constant numbers, and then t is your parameter value, and you let t be various things. And we can do the same thing for y and for z. Okay, so now to give a little bit more of a concrete example, in 2 dimensions, you might have had something like this. Okay, where the idea is you let t be different things, and then that sketches out a graph because it produces points in x and y, and so you get a graph, and this one turns out to be a line. So we want to take that same idea and expand it to 3 dimensions, but the way we're going to do it is we're going to express it as a vector. Okay, so it's the same idea over here, where this vector r is going to be x, y, z. This vector r0 is going to be x0, y0, z0. So just some initial vector. And then this vector v is going to be like this: a, b, and c. And so this is a vector equation that contains all the information that you would get out of a set of parametric equations. Okay, so it turns out that a line in 3-dimensional space can always be expressed this way, where r0, this is what we call the initial vector. Okay, so the vector when t is equal to 0. And then v is what we call the direction vector. All right, so here's how this works. You start off with r0. Okay, so that's this guy right here. So you start off with r0, and that is a vector pointing to an initial point along this line. And then you take your direction vector v, and this direction vector v needs to be going in the same direction as you want your line to go. Right? So if I kind of try to translate this up here, here's v. Okay. And then the idea is we are taking r0 plus some multiple of v. Okay, so if we multiply v by something, it either gets longer this way, or shorter, or it goes back in the negative direction if t is negative. But either way, what ends up happening is that you are taking this vector plus this vector, so this gives you another vector that goes from the origin to here, and that's your r. So in this case here, the v gets multiplied by something, extends all the way out, so this plus this gives you your r. Okay, so the way to think about a vector equation for the line, here's what helps me, is that the vector equation is giving you this vector r, which is the pencil that is sketching out the line. And this pencil moves and elongates and shortens in order to draw this line. And so here's an illustration of that. So think of the red vector here, and you can kind of see where it's at. See how y equals 0 is there, z equals 0 is there, x equals 0 is there. So this is the origin right down here. Okay, so that is our r that we're producing. And so the idea is, as I put in different values of t, it changes the direction of r, it changes the length of r, and I like to think of letting t be different things basically allows this r vector to draw the line that we're trying to draw. So the equation is literally giving you the kind of, it's like a magic pencil that changes length, changes direction, and as it does so, the tip of it draws out your line. All right, so down below here, here's what I already actually wrote up there. So first of all, here written out is your vector equation, x0, y0, z0 plus t times abc, where abc is the direction vector. You can kind of think of the direction vector kind of like you think of slope, you know, in your past experience. The parametric equation for the line, so this would be just me listing out the x, the y, and the z separately, but it's the same information. All right, so let's do one example here. It says find a vector equation and parametric equations for the line that passes through the point 1, 3, 4 and is parallel to the vector 3, negative 2k, or 3i, negative 2j plus k. So this point here, if it passes through this point, here's what we can do. We can take this point and we can say R0 is equal to 1, 3, 4. And then if we want to be parallel to this, parallel to that means that's our direction vector, right? Look, go back and look at the diagram, right? The line is always parallel to whatever the direction vector is. So that is going to be our direction vector. So we'll say V is equal to 3, negative 2, 1. So writing out the vector equation would be to say r, and it's a function of t, is equal to 1, 3, 4, right? That's r0, plus t times 3, negative 2, 1. There's our v. And to put it together, 1 plus 3t, 3 minus 2t, and then 4 plus t. So there's our vector equation, and then parametric equations are just me writing out each one separately. So there's our two different representations here. So that's our vector equation. And these are our parametric equations. All right, now there's one other way that we can express the equation of our line, and that is through the symmetric equations of the line. Okay, so if you take your parametric equations and just kind of jot this over here. So you take your parametric equations, x equals x0 plus at, then you can solve for t. So x minus x0 equals over a equals t. But you know what? If you started off with y equals y0 plus bt, you could do the same thing for this t. So I don't need to do it again, I don't think. But I think you'll believe that that can be written as y minus y0 over b. And then with z minus z0 over c should be t. So all three of these are all equal to the same t. And so that must mean they're all equal to each other. So this is called the symmetric equations for a particular line. Okay, so example 2 then says find a vector equation, parametric equations, and symmetric equations for the line that passes through these 2 points. Okay, so here's one of those situations where it's good to make a little sketch, but don't worry too much about trying to put it actually on a graph or anything. Just kind of try to represent this idea that you know that you want it to pass through these 2 points. Don't worry about the accuracy of this. Okay, so let's think about how do we come up with the equation for this. Okay, so remember what we're looking for, right? Right, on our diagram on the previous page, right? We need an R0 and we need a V. Okay, so, you know, and again, I'm not trying to be accurate, but let's just pretend like this is the origin here, right? Here's the origin. So the idea is I need to have an initial vector that goes to one of these points. So that's, you know, going to be my R0. And then I also need a direction vector that is parallel to these, right? That would be my V. But as you can see, I know how, right, to make a vector if I know 2 points, right? I just subtract these. And then R0, if it's starting at the origin, I can just express R0 as being 4, 10, negative 6. And then, of course, V can be 7 minus 4, 9 minus 10, 2 minus negative 6, right? Just subtracting these points, x, y, and z values. So my direction vector then is 3, negative 1, 8. And so that's enough just right there. So I can say that R of t is going to equal 4, 10, negative 6 plus t times 3, negative 1, 8. Or if you'd prefer it as just a single vector, 4 plus 3t, 10 minus t, negative 6 plus 8t. So there's our vector equation. All right, give myself a little more space here. And then, of course, the parametric equations are pretty straightforward because it's just taking these but writing them out as x equals, y equals, and z equals. So x equals 4 plus 3t, y equals 10 minus t, and z equals negative 6 plus, that's right, that's supposed to be a plus there, plus 8t. So there's our parametric equations. And then our symmetric equations. So remember that is going to be just x minus your initial x value divided by the x component of the direction vector is equal to y minus the initial y value divided by, in this case, negative 1, because that's the y component of the direction vector. And then z minus negative 6, I'll go ahead and put plus 6 divided by 8. So those are our symmetric equations that get across the same information. All right, now one trick, and this is a really handy trick, especially I really recommend this, especially just to kind of log away in your mind for Calc 4. This will be something that you will use a fair amount in Calc 4, and that is if you want a line segment only, okay, just a line segment that goes between 2 points, okay, or I guess you could say goes between 2 vectors, then what you can always do is take 1 minus t times the initial vector plus t times the terminal point vector. So here's what I mean by that. If here is a point and here is a point, you know, and this is R0 and this is R1, then I know I can make a line that goes through there, but let's suppose I only want a line segment. I want the line to start here and end there and go no further. The way you do that is like this. And the reason is because, and if you only let t go from 0 to 1, then when t is 0, then what you're going to have is 1 times R0 plus 0 times R1, right? So you're going to have none of R1 and all of R0. And then when you get to 1 at the end, that's when you're going to have 0 R0 and 1 R1. So then you have only this at the end. And so by letting t go between 0 and 1 and setting up the equation this way, that ensures that you just have a segment that begins at R0 and ends at R1. All right. So let's, in example 3, it says find where your line from example 2 intersects the xy plane. Okay, so the line we were just talking about, so let me just write down the equation again. I'll just write down the vector equation is fine. So r of t is equal to 4 plus 3t, 10 minus t, and negative 6 plus 8t. All right, so let's think about what do we know about the xy plane? Is there anything special we know about it? Well, the xy plane is the place where z equals 0, right? So if z is equal to 0, we can set z equal to 0, which means we take the z component, set it equal to 0. So 8t equals 6, t equals 6 over 8, so t is 3/4. So what that tells me is that t, our parameter value, must equal 3/4 at the moment when z equals 0. So then we can take our x component and say, okay, well, what does our x component equal when, oops, sorry. So 3 times 3/4. So I'm just plugging that t value in for my x and 3/4 in for the t value in my y component as well. So x equals, I'm going to need a common denominator, so this will be 16/4 plus 9/4. So x equals 25/4. And then y equals 40 over 4 minus 3 over 4. So y equals 37/4. So with all that, and I kind of ran out of room, but where does your line intersect the xy plane? It would be at the point 25/4, 37/4, 0. All right, so in example 4, it asks us to find a vector equation, parametric equations, and symmetric equations for the line that passes through those 2 points. All right, so here's where what I would suggest is to use what we learned on the previous page. So, and now as I'm doing this example, I'm not sure why I didn't make this example 3 and follow up the previous page with that, but oh well, I'm not going to change it now. So back here, what did we say? We know how to make a line that goes between 2 points by setting it up this way. We can do the same thing here, right? So we can kind of think of this first one as our R0, and we can think of this point as representing our R1. I know this is a point, not a vector, right? But our vector can be the arrow going from 0, 0, 0 to 5, 3, 1. And use this, right? R of t equals 1 minus t times R0 plus t times R1. Now, on the previous slide, the thing that made it only go from R0 to R1 was because we only let t go from 0 to 1. But if we let t be whatever it wants, then we'll get a full line that goes wherever it wants. So here we're just not going to put that restriction on it, but we'll still use this same formula. All right, so I can say R of t is equal to 1 minus t times 5, 3, 1 plus t times 2, 1, 1. All right, and so as I do this, we'll end up with 5 times 1 minus t, 3 times 1 minus t, 1 times 1 minus t, that's the first vector, plus 2t, t, and t. So here it's 5 minus 5t, 3 minus 3t, 1 minus t, plus 2t, t, t. And then we can put those together. So 5 minus 3t, 3 minus 2t, and then just plain old 1 there at the end. All right, so there is our vector equation. Okay, so then our parametric equations are x equals 5 minus 3t, y equals 3 minus 2t, z equals 1. But how about our symmetric equations? Okay, this might be kind of awkward because we're used to taking our symmetric equations and saying, okay, well, let's take, x minus some initial x value, which I'll say is 5, over the negative 3 is equal to y minus 3 over negative 2, but then there is no direction vector component for z, right? Because it's just 1 here. So if that ever happens to you, then your symmetric equations are going to be just these two with the extra statement by itself, z equals 1. Okay, so I wanted to show that example, so if you ever run into that, you know how to deal with it. All right, so we used this nice little trick at the beginning. Earlier we did an example where we found the line that went through 2 points, and we did it differently, remember? Remember, we found a direction vector first and then picked one of them to be our initial vector. So can we just agree here that everything would have turned out exactly the same? If I was going to find my direction vector v, I would have said something like 2 minus 5, 1 minus 3, 1 minus 1, which is negative 3, negative 2, 0. And those are the exact A and B that I actually ended up with, right? So this is just a different way of getting at the same thing, and you can decide if that's the way you want to go about a problem like this. All right, so one more example, looking at a couple of lines here. So this time we're given the parametric equations for 2 lines, and we're asked, do these lines intersect? Okay. Well, these 2 lines, of course, intersect if there's a spot where their x, their y, and their z are all the same. Now, if we're talking about 2 lines at once, we don't want to use t for both of them, right? So I'm using s as my parameter value here. Okay, so what are we looking for? We're trying to figure out if there's a way to make -6 minus t equal 5 plus 2s. Can the x's be set equal to each other? So there's one equation. And then at the same time, the y's need to be set equal to each other. And then the z's need to be set equal to each other. So we can pick any of these. It doesn't really matter. I kind of like maybe starting with 3. So number 3 would tell me that 2t must equal 4s, right? Because there's a 1 on each side, so subtract 1. So t must equal 4s over 2, which is 2s. Okay, so that's a good piece of information. So then I can go to equation number 1 and say, okay, instead of t, I'm going to write -6 minus 2s instead of t equals 5 plus 2s. All right, so add 2s to both sides. So -6 equals 5 plus 4s. Subtract 5. So -11/4 must be s. Okay, so let's see. Does that work? Okay, so if -11/4 equals s, then this tells me that t, which is supposed to equal 2s, must be -11/2. So does that work in equation 2? So equation 2 says 20 plus 3 times my t value, which is -11/2, is supposed to equal -9 minus 4 times s, which is -11/4. So that's 20 minus 33 over 2 is supposed to equal -9 plus 11, which is 2, which definitely does not work, right? So that leads us to equation number 2 not working. So the fact that we could not make all 3 of those equations work means that the lines do not intersect. Okay, now let's take a look at a graph of these lines. All right, so I'm going to use the same program I showed you that initial demonstration on, but let me just get rid of everything, okay, and kind of show you how this thing can work. So there's all sorts of options to select. We're going to make a space curve, so I'm just going to try to graph the 2 lines and make sure that I'm confirming that no, they don't quite intersect. So I'm going to click space curve, R of t, and then I'm just going to plug in the equations for x, y, and z. So -6 minus t, 20 plus 3t, and then 1 plus 2t. And again, this is just on the course website, right? The link to this tool here. All right, and now we need the other one. So a new space curve. And this one it does allow me to use t for both of them. So instead of 5 plus 2s, I'll say 5 plus 2t, which is okay when I'm just graphing them, but definitely wanted to have different letters for the algebra we were working out. All right. And then sometimes, like right here, this line fell short. That just means I need to involve more t values. So, this one I'm going to maybe change from -10 to 10 instead. And then, maybe it was this one I wanted to change. -15 to 15. All right, so now I can see, if they cross, I can see where they might cross. And look at that. That is unclear, to say the least, right? And so one thing that I could definitely do here is I can change the XYZs they're showing me, because look how big this is. No wonder I can't really tell whether they intersect or not. So what I can do is go to bounds, and I can say I want them fixed. And when you let them be fixed, then it kind of goes automatically for -5 to 5 for all of them. And now look at that. Now I can see, right? I can see there's definite space there, and so so because of that, I'm now confident that I did that algebra correctly, because there's clearly space in between those lines. All right, so let's move on down to part B. So they're asking, are these lines parallel? Okay, are these lines parallel? Well, if the lines are parallel, let's write this out. If the lines are parallel, then the direction vectors, right, must be able to show that also. Okay, so then the direction vectors should be just multiples of each other, right? Scalar multiples of each other. And so if I look at those, -1, 3, 2, that is not a multiple of the other direction vector to -4, 4. In other words, I can't multiply this entire thing by a number to make this. Okay? Or another way to say it, or if you prefer, you could say that they're cross product, right? Remember that two vectors are parallel if their cross product is the 0 vector. Their cross product, I'm not going to check it here, we'll say is not the 0 vector. So either one of these tells us the lines are not parallel. Now this is interesting because in 2 dimensions, remember, if you have two parallel lines, or excuse me, 2 lines that aren't parallel, then they have to intersect. Well, that's not the case in 3 dimensions. You can have 2 lines that are not parallel and they do not intersect. So these lines are called skew lines. They may not be parallel, but they don't intersect. Or another way of saying it is that they cannot lie in the same plane.